Hello, my name is Mark Dufour. I'm a research fish biologist with the USGS Great Lakes Science Center. In 2023, a group of researchers led by Peter Esselman deployed multiple autonomous vehicles on Lake Erie to evaluate their use and support of fisheries management efforts. The effort here complements similar work occurring on Lakes Michigan, Huron, and Superior. Two different types of autonomous vehicles were deployed on Lake Erie, including an uncrewed surface vessel designed by Saildrone and a long-range autonomous underwater vehicle designed by the Monterey Bay Aquarium Research Institute. Today I'm going to focus on the uncrewed surface vehicle, which is shown here being towed out of Erie, Pennsylvania to begin its mission during July 2023. So, what is an uncrewed surface vehicle, specifically the Saildrone Explorer? Well, it's not a small vessel. It's 23 feet long with a 15-foot rigid sail and a 6-foot deep skeg. It's bright orange and highly visible on the water. The vessel is powered by internal batteries that are charged daily through solar panels and propelled by wind, allowing the drone to remain at large for over a year if needed, and traveling at, on average, 3 knots. The drone carries a host of sensors that record both surface and underwater environmental conditions during the mission. But of greatest interest to us was the ability to install a hydroacoustic system and collect fisheries related information. For perspective, here's a picture of the Lake Erie drone SD-1080 waiting at the dock in Erie, Pennsylvania for deployment. How does this vehicle move? Well, the drone is tasked with daily missions, and we have an example here from one of the upper Great Lakes. A series of coordinates are remotely communicated to the drone, and the drone automatically adjusts its rudder and sail to consecutively achieve the waypoints, transiting from one to the next. Biologists work with Saildrone's mission control to adjust daily routes, and the speed and precise location of the drone are dependent on wind and wave conditions. We are particularly interested in using fisheries acoustics from autonomous vehicles because acoustics provide a unique perspective on the distribution and abundance of organisms in the water column. It does this using sound, where a pulse is produced and echoes from objects in the water column are reflected back to the system. This can generate measurements from the water column over large temporal and spatial scales. Here we have a cross-lake transect from Lake Erie, where we can see the surface, the bottom, and the thermocline, as well as fish and zooplankton distributed among them. Hydroacoustics are used across the Great Lakes to assess pelagic prey fish abundances. However, these surveys are typically carried out by large, noisy research vessels, and there is some concern that fish may avoid the vessel's path and cause negative bias in survey estimates. In contrast, the uncrewed surface vehicles are effectively silent. So we decided to compare fish density measurements from the two platforms to evaluate if there was any related bias. So what exactly did we do with the Saildrone? Well, we launched it from Erie, Pennsylvania in July 2023 and began our mission on August 1st, collecting data for 58 days until September 27th. You can see the Saildrone's orange track here on the map, spanning the length of Lake Erie. During this time, the Saildrone interacted with 4 different agency vessels, including Ohio DNR's Almar, Ontario Ministry of Natural Resources Erie Explorer, Ohio DNR's Grandin, and the USGS Muskie. Locations of these interactions are depicted with dots on the map. We also collected more intense data from 3 different locations, associated with secondary objectives in the west, central, and east basins. In total, the USV, or Saildrone, collected around 3,600 kilometers worth of data. When I say we interacted with vessels, what I mean is we performed overtakes, a total of 51. An overtake involves collecting paired samples between the vessel and the USV, where on a given night, the USV was tasked to collect data along a straight line. The vessel, which moved much faster, would then follow the USV until it reached and overtook, at which point the vessel would move off transect and the USV would carry on. Once the USV traveled 2 kilometers, the vessel would return to transect and begin collecting again. This generated 2-kilometer transect of paired USV and vessel data. Here we have an example of some of that paired data, where we can see dense aggregations of fish from both platforms. From this data, we calculated fish density and then compared the measurements statistically to evaluate correlation and differences in magnitude. So what exactly are we looking for in the paired data? Well, 2 important characteristics are how strongly the data are correlated and if there are any measurable differences. Here I have a made-up data set just to illustrate how the data would look under different conditions. If we plot the individual overtakes, data with perfect correlation and no difference would have parallel lines connecting USV and vessel measurements. If we had perfect correlation and differences in magnitude, then we would still have parallel lines, but the point clouds would be shifted from one another. And if there was imperfect correlation and differences, then we would have non-parallel lines and shifted point clouds. Another way to look at this same data is through a bivariate plot. This is where the vessel data are plotted on the y-axis and the USV are on the x-axis. So with perfect correlation, all points would fall along this 1-to-1 line with no difference. With perfect correlation but a difference, we would have a straight line shifted off the 1-to-1 line. And if we have imperfect correlation and differences, then we would see a cloud of points that were shifted off the 1-to-1 line. Here we're showing the paired USV and vessel data from the overtake study. We can see that there is imperfect correlation between the individual overtakes, which is not unexpected, but there doesn't appear to be a strong difference between the measurements overall, as the point clouds are not dramatically shifted from one another. When we look at the bivariate plot, all the points fall along the 1-to-1 line without too much spread, which is a good sign. However, if we look closer at the bivariate plot, we can see that there are some groups, potential groups of data that are behaving differently. And when we identify which vessel and portion and time that those points were collected, we can see that there may be some need to explain. To quantify these differences, we used a hierarchical bivariate normal model. This allowed us to simultaneously quantify correlation, magnitude of differences, and uncertainty between individual vessels and USVs at the time and location of the overtakes, as well as the same metrics between the different groups. The between group comparison represents more of a survey level scale comparison, which is greatest interest from a management perspective. Looking at the results on the right, we see that all of the groups have fairly strong correlation, as the 95% confidence ellipses are elongate and follow the one-to-one line. Also, the mean estimates, or these larger dots with crosshairs, mostly fall along the one-to-one line as well, which is a good sign. However, there was one overtake scenario that was a little bit lower than we would expect. This occurred with the USGS's muskie during collection in the eastern central basin. Using the model results, we can summarize the differences with the correlation coefficient and calculating the proportional difference between USV and vessels in each group and between groups, or what I'm calling the survey level here. Starting on the left, we see strong positive correlation between paired estimates at all levels, as estimates fall between 0.5 and 1. In particular, the survey level correlation remains strong, which is a great sign. Moving to the right, we see that proportional differences are variable. What we'd like to see is all vessels falling near or spanning the one line. However, the muskie in the eastern central basin was substantially lower. The difference appears to be situation specific, since we did not see as large a difference from the muskie when it sampled in the western basin at a later date. Most importantly, the survey scale differences are relatively small. This is a good thing, as it indicates on average measurements between the two platforms would likely generate proportional estimates. There doesn't appear to be systematic vessel bias, which is a good thing. However, there were some differences associated with the location and timing of USV vessel interactions. These were most likely caused by other interacting factors. For example, we sampled over a wide spatial scale in a 2-month period. Although our samples were temporally and spatially paired, Lake Erie is a dynamic environment. Changes in trophic status, depth, species composition across the lake will impact the spatial temporal heterogeneity of fish distributions, and uneven distributions of fish are likely impacting the comparison data. Luckily, moving forward, this can be mitigated by collecting more data over wider temporal spatial scales to average out these types of differences. Also, the survey conditions across the study varied quite a bit. The period in which we saw the greatest differences occurred when the wind and wave conditions were less than ideal. This caused the USV to pitch and roll more than the survey vessel. Also, in rough conditions, the larger vessels can be more impacted by air bubbles that are entrained in the surface layer, both of which degrade acoustic signals. Luckily, this can also be mitigated in the future by restricting survey data collection to more ideal sampling conditions. The work of the advanced tech team strives to support fisheries managers and facilitate decision making. Hydroacoustic sampling, particularly when deployed from an autonomous vehicle, could enhance current monitoring programs, contributing to Lake Erie fish community objectives as outlined by the Lake Erie Committee. I'm going to briefly highlight 3 opportunities next. First, USGS and partner agencies carry out an annual pelagic preyfish survey, which includes both midwater trawling and hydroacoustic measurements. Here's a map of the distribution of samples across that survey. Currently, due to logistical constraints, we are unable to collect enough paired midwater trawl data to apportion hydroacoustic data from across the lake to species and calculate biomass. Supplementing hydroacoustic data collection with a USV may allow vessels to transition to more midwater trawling while simultaneously increasing the spatial coverage of hydroacoustic data. This would help improve characterization of the preyfish community and in time allow us to identify associations with biological and environmental changes. Second, hydroacoustic sampling does not have to be restricted to preyfish surveys. We can also use it to look at large targets like lake trout. Paired with autonomous platforms, we can evaluate deal movements over large spatial scales. During the 2023 effort, we collected hydroacoustic data associated with the interagency coldwater gillnet survey. Paired hydroacoustic and gillnet data could help quantify distribution and abundance of important species like lake trout, assess gillnet survey efficiency, and all of this could help benefit restoration efforts. Finally, we can use these tools to better understand distribution and abundance of intensively managed species like yellow perch. Specifically, during 2023, we collected hydroacoustic data from the Saildrone as well as 2 long-range autonomous underwater vehicles in areas impacted by harmful algal blooms and hypoxia. This data is paired with bottom trawl surveys, and the results could help communicate the impact of these disturbances on fish distributions. With the vessel comparison work, we've shown that an uncrewed surface vehicle can collect complementary hydroacoustic data. That was the first step. Moving forward, we see several opportunities where autonomous vehicles and hydroacoustics could contribute to management efforts, all of which enhance existing surveys. There's a lot of work yet to be done, but we think that the technology has great potential. The 2023 efforts on Lake Erie required a great deal of planning, coordination, and cooperation. I want to directly thank those listed here and many others who have helped thus far. If you have any questions about this study or our plans moving forward, please reach out. Thank you.